presence of a Lewis acid, compound 1 rearranges via intermediate 2 to afford compound 3. So we have hexagon here, and then it's now becoming the heptagon. Draw curved arrows showing how 1 is transforming to 2, and then note that Lewis acid has been left out for simplicity. Okay, we don't really need to be concerned with it. I will show you why. So we have the left side that's very intact, and then the triangle is still retained. The only difference between compound 1 and compound 2 is that we now have a acyclic compound in which there is no more ring structure, and we have a double bond between the carbon and the oxygen. So let me draw the lone pair around the bottom oxygen. The formal charge should be 0 because I have 4 lone electrons and then 2 bond, so that just turned out to be 0. But on the compound 2 we form plus sign there, so, and then we should create a double bond. So we could play the lone pair as the nucleophilic attack on our bond here to create double bond, and then that bond between the oxygen and the carbon, which is attached to the phenyl group, can actually be broken, and then place the head of the arrow on the oxygen to create the negative formal charge. So we now have an acyclic compound that answers our choice A. Another interesting way to solve this was, instead of thinking this as a concerted process, we could actually have the leaving group as this bond breaking first and then create the carbocation. So let me illustrate that. So what I mean is I could have this first, okay, that's gonna cause the carbocation on that carbon you see right below here. Plus sign, and then there is a hidden hydrogen, by the way. Now because the bond is broken and the electrons are located on the oxygen atom, we should have a formal charge of -1, and the triangle is still retained on the top. Okay, now we could place that lone pair onto our bond here as 2, and then create the resonance structure that makes the compound 2. And now he becomes plus on this oxygen for the formal charge. Okay, notice that that's same as the compound 2. So if this is compound 2, this is also compound 2. And you might ask, well, it is preferred. Thing is, this is not really preferred because this form is preferred. Let me explain why this is more preferable. Okay. We don't have octet on this carbon, but if you notice, we have octet for carbon, and you gotta notice that there is hydrogen hidden here. or implied hydrogen on the carbon, and the oxygen has 8 electrons around. You have a double bond on the right, single bond, and the lone pair. So octet always trumps over the former charge, because you might say on the left structure we have a plus sign on the less electronegative carbon instead of the oxygen. So based on electronegativity, you might say the left structure is more favored, but no matter what, for our carbon, nitrogen, oxygen, fluorine, the second row always is more preferred to have the octet. That comes first and then former charge. So either way, you're gonna get the same answer. So I say the concerted process is probably better, and you'll get full credit for that. Now B is more tricky because it's the same. They're asking the same thing, except you have to kind of visually observe this. So how do we turn these 2 and 3 and show the mechanism? Well, looking at that, if you can kind of visually, see this, you can have, you notice that there's no plus charge on the oxygen in compound 3, and then double bond is gone, and in this time the acyclic compound becomes a cyclic. So I'm gonna have to do something about that bond here. Okay. And also the oxygen, which is most likely on that ketone here, gotta have a double bond. So let me draw the lone pair. That probably have to go toward this carbon oxygen bond so that we get the ketone CO double bond. And we gotta break that triangle ring and then create a larger main ring. And we also gotta break that double bond here. One way we can do is bring that, because now our carbon has the 5 bond, right? Because we have double bond here and single bond, 2 single bonds from the triangle and 1 single bond from the left side. We can form 5 pair of electrons. Therefore, that has to come down and attack what? The carbon here. This becomes a nucleophilic, as you saw on our lab structure here. Right there, you see the nucleophilic there. Okay, it's very probable. So we're gonna form a bond and break that triangle, and then now we just have a single ring structure instead of 2 ring you saw in the compound 1. And then our carbon has again the 5 pair of electrons, so we gotta push this single bond and then place it on the oxygen. That way we have a net 0 formal charge on that oxygen. And also we're gonna form 7 side or heptagon, because by breaking that triangle and then attaching that to the carbon, see, we're gonna have 7 side. So I can count that 1, 2, and then 3, 4, 5, 6, and then the new bond becomes 7. So we have a 7 heptagon here on the compound 3. Now in case you can't really see this, other than making the molecular model kit, here's one easy way to visualize. You can actually rotate a single bond. Remember that unlike the double bond or triple bond, which cannot enable the rotation of the around the or about the bond to create many conformations, single bond actually allows us to have multiple basically infinite, under normal circumstance, infinite number of conformation. Remember that Newman projection, for example, was one such an example that illustrates that. I'm gonna rotate this bond, so let me color that bond, that green color. I hope you can see it. Maybe light green. Yeah, you see that bond that can be actually rotated because we are no longer in the ring structure in compound 1. In compound 2 it's acyclic, so I'm gonna rotate that. And then you're gonna notice that oxygen is now on the other side because I rotated 180 degrees. And then the triangle will, okay, you can draw the symmetry here. That will be on this side. So we'll have something like this. Okay. It's like drawing the symmetry in math class, x equals y, and you're just making a mirror image. Okay, so we have this structure. Now this might be easier because we can now see the flow of electron from the lone pair on that oxygen. Okay, make a double bond to create ketone. And then we can break this. Now, here's an important thing. You cannot break this because that would create the methyl group, and then you're not gonna have the heptagon. To create heptagon, you have to break this bond here. You see the red color I just made. So that need to come attack our nucleophilic or our electrophile center, and then that's gonna push this the electron of the bond and then create a net formal charge of 0 for our oxygen. And that's gonna create, in turn, that's gonna create the compound 3.